We are recording.
We are recording. Okay, so
No, wait,
literals.
pause. Pause there. Unpaused. Literals, right?
Yeah, it feels like it's been forever since we did anything other than squashing bugs.
Squashing and defeating the bugs. Okay, so I have a question. Does the book treat uh,
The book doesn't say
numbers?
anything about numbers.
Okay, so we are on our own creativity to make that happen.
Yeah, the book it gives us
Well, but that's
some optimized instructions for add-ons specifically, but not for other types. Oh, for
but
lists as well.
yeah, but I think that should be fairly straightforward because it's essentially parsing, code generation, and equality for unification, right?
Uh, we also need to introduce primitives um, to do arithmetic because, like, hmm, actually, should we? Do we?
I don't. Well, we should, but not on the same goal. I think we should first start by having them in the language, and then compare some working and stuff like that, and then we just swap the nil with a zero and see if things work in our examples.
Okay. Let's see. We need to do.
Parsing. So you need to open the MLI.
Oh my,
MLY actually. The one that we defined the grammar.
this one,
Well, no, this is what's going to generate the parse. So we need to go to the token thingy.
the Lexer.
Yeah, yeah, we have digits already, which is cool. We have digits. Okay, so I think you can add a new rule on line 24, and you just put digit, and let's see.
Digit.
Yeah, like we have identifier and white spacing and new line. You just add a new one called the digit.
But we already have like integers here, don't we?
Well, we can use that as well. We can use that as well. It's just because I'm a little bit afraid of having negative numbers in the first, in like from starters.
Why?
Well, I don't know. I never made a real compiler before. And it turns out
Dude,
that you can do a lot without negative numbers.
yeah, you can, but like, uh, technically, the native number type for most computer systems is actually the signed integer, not the unsigned one, because the industry has pretty much standardized on choose complement for signed arithmetic.
No, yeah. No, let's go with the integers there. That's fine. But it's like I just wanted to be noted that like Zozin did 20-ish sessions of Porth without negative numbers. He made sockets work before having negative numbers or something like that.
Well, you don't need negative numbers to handle byte streams because you can just use 0 to 255, and you don't really need negative numbers for indexing either.
Wait, is that how you do that though? Because I think you said integer int. I don't think that's how that works. It should be int on the left because that's what line 17 is doing. I will
Int on the
be
left.
Yeah, int on the left. I will be back. Keep going though. Keep going.
Hmm. Man, is it wrong that I kind of wish this was just a recursive descent parser? Uh, let's see. We have digits. We have int. We have white space, new lines, indents, upper indents, integers. We have query. Okay, this becomes a query. This becomes hmm. Yeah, maybe this is actually, yeah, Lemos is right actually. Hmm. Now how do I do this? Lexing. Something like this, I guess. This should work, right? Hopefully. There's no constructor integer within type token, apparently. So okay, it exists, but it is unused, apparently. Okay, so how do I list identifiers, functorial lam? So I guess we can just do something like, I don't know, integer. An integer. And then we need to I guess just do something like, I don't know. Actually, we need to add something to the AST, right? We need to say an expression is a variable or a functor, or it can now be an integer as well. Integer of int, I guess. OCaml int type. Hmm.
I'm back.
Hello, Lemos.
Okay, so what did I miss?
I'm adding a new node type to the AST because we need something to hold integers, right?
Yeah, just call. I would just call int in caps.
The standard library also provides int32 and int64 modules, blah blah blah. Bitwise operations treat the signed bit the same as other bits, which is okay, I guess.
Yeah, I think we should go with int. Later on we can specialize on int32 module or whatever. Just to make it work, int seems enough to me.
Yeah, so integer of int, and then this needs to be an ast.integer with this, right? Something like this, I think.
Yeah, it's definitely something like that, but here's the question. Where are we gonna put this thing?
What do you mean?
Exactly that. Where are we gonna put this integer identifier on line 53? We need to put that in some of the recursive parsers. So where can we have an integer? I guess that's the question.
Well, anywhere where we have a functor or a list, I suppose.
Well, functor is line 28. 27, I guess. That's the rule for the functor.
Okay, a program is a declaration followed by a program, or a query followed by a program, or an end of file. A program, where is program defined? Oh wait, no, this is recursive.
Yeah.
Okay, declarations and queries. Declaration is it's either a functor followed by a dot, or it's a functor that holds. This is a terrible name, by the way.
No,
Followed by
I
statement.
think I disagree. I think I like the holds because to be the arrow. And then we have a separated, a non-empty separate list of statements. Yeah, so we need to change the functor lem, essentially.
Yeah, then we have a functor name, which is an identifier, followed by a left delimiter, followed
Yeah,
by a list of
which is
identifiers.
44.
But actually,
Um, oh, you might not want the end of file there in this recursive thing.
this is for the
You
entire
probably,
program though.
yeah, but I mean, it is on the same level as other constructs. You probably want something like uh, a structure that describes the list of the things you have on the top level, and then you have this
But
and
that's what
end of
this
file.
is. That's what this is actually.
Yeah, but I think Nathan is not liking the name program, I guess.
No, that's not what I mean. Uh, there, can't you like have end of file multiple times or end of file and then other stuff by the structure there?
No, you can't.
How?
Because this is a recursive definition, Nathan. A program is either an end of file, or it is a query followed by
Hmm.
another program, or it is a declaration followed by another program.
Yep.
Oh, okay, I see.
I'm starting to
Yeah, I
think
see.
that numbers should go into the list identifiers.
Hmm. Okay, if this is a right delimiter, if this is an upper
Comma.
identifier.
Yeah, this is to get the list of stuff. This is to get list of stuff. Our case is pretty much going to be similar to line 49 in a way, because it's
Mm,
essentially that, but it's integer. Yeah, I think that's it.
we can have default values, right?
Oh, sure.
Okay, let me fix something that's been bothering me for a while now.
Are you gonna remove
Uh,
the brackets from the zero arity things?
I'm going to make them optional actually, because that's how they should be.
Oh, that's fine.
Although if we're not careful, this might introduce ambiguity, and we don't want that.
Yeah, for now I would just grab line 54 and put immediately after 46. Well, yeah, 45 actually. And call it a day. And see if this parses.
Uh, Marinho, are you guys having warnings when compiling this?
Of course not.
Because I'm not. Yeah,
No, this
I'm
is
not.
new because I just introduced this token.
Mm, I mean, how are you running the generation for the parser? Because I'm not even sure if it has the warnings by default, and I don't
It
remember how it.
it does not come the warnings by default, but I removed the warnings. I can put them back.
Yeah, because
Mm.
I don't remember how much it complains about look aheads and stuff. So it might be complaining because it might be doing a lot before it can distinguish the declaration
Yeah,
from
that's
query.
definitely possible. Definitely possible. We can investigate that after parsing number, folks. Uh,
Actually, let's make these things a little bit tidier because right now this is kind of a mess. So an expression is either an upper identifier or we need to up, um, we need to create something in this case, right?
I'm not sure yet what you're trying to achieve. Can you explain first, Maria?
The problem is that the definition of an expression is not explicit here. It's kind of mixed together with a list of identifiers. And that's kind of terrible, actually.
Yeah, the reason that we did that is to get around the problem of the closing delimiter. So we start with the comma on the on line 35, right? And then we statements. No, wait. No, I said not correct stuff. No, yeah, it is that. Line 28, we open a bracket and we let the list identifiers to close it, the bracket. That's why we did this way. Because then we don't have the problem of the closing bracket. Classic parsing problem.
Well,
Well, man, I don't know. I don't know if we should tackle this right now. If it's easy enough, sure.
like if this was just a recursive descent parser, this would be a breeze, but it isn't.
Well,
Okay, let's try something like this. It's an upper identifier.
yeah, it's not trivial to unify all of these in an expression. They are very finicky. So if you have an upper identifier with a comma, then we call ourselves. If it's an identifier with a comma, we also call ourselves. If it's a functor,
No, that's because this is the recursive case. Those are the recursive calls. It should be something like it's either a right delimiter or it's an expression, a comma, and a list identifiers. Something like this.
okay, I propose we first integrate the integer, then we optimize it to look better. So I will just put line 55 immediately after 45 and call it a day. And that's what I would do just to make it work. Yeah, this was just gonna complicate stuff because that's not how you do that. You need to grab the output out of this integer subparser as we're doing on 49.
So you mean like this? This is 3, right?
I I believe so. I believe so, yeah. I believe so.
Actually, this is not quite right. We need to parse the integer here because this is a string at this point, right?
Yeah, we probably
Uh,
need to translate string of int. Well, int of int. Wait, it's the opposite, right? We don't want to do to stringify. We want to unstringify.
can't we just call it?
Yeah, but I don't know if this function exists.
I think it does.
Yeah, it does exist. Okay, let's write a program now that uses an integer and see where it breaks in the code generation. Let us make the compiler tell us what is wrong.
One moment. Have an integer.
I probably would not make this subparser called integer. I would make it number, and then later we can add rationals and stuff.
Hmm. Yeah, actually, I think making this work with an expression is not that hard. If we do this, right, then we can say it's an integer or it's an upper ident, in which case we need to grab this and put it here.
Yeah.
Oops. And that means we can get rid of this. Or we can make it be an ident.
And then you need to grab that thing there.
In which case we grab.
47.
Why do we
For,
have ident and write delimiter?
uh, uh, well,
Like that's kind of redundant.
no, it's definitely not. One of them is having functors within functors, I guess, and the other one is just a closing bracket of a functor that just closed.
No, but this is kind of redundant because this should be dealt with by having the recursive case here. Oh, it's because of the freaking comma.
Oh yeah,
Because
of
of the
course.
freaking comma.
Yeah, in one of them you are combining the identifiers, like I said, functors inside functors, and the one on you're about to close a functor.
Well, in that case, we can do this, I suppose.
That works.
So we have integer, we have upper ident, we have ident. And we need a functor element as well.
Yeah, functor element. Well, you
Uh,
can say that a functor is an expression, I guess. That's kind of what we are looking at. Yeah, why not? Just copy 48 or 40, the beginning of 48 or 49, and return the ast.functor.
hmm.
No, you don't need the comma and you don't need to copy that part because this is already being dealt by 46, 47. Just copy the functor lm.
Okay, I guess we can do this,
And
and
then the
then this becomes.
ast.functor functor lm. No, you need the no, actually that's it. Actually. Yeah, now you can remove 48, 49 and maybe this works.
It does.
How impressive would it be that this program works but one of the other ones they don't? Because
What do you mean?
well, yeah, we have 4 programs. I would test this change with all 4 of them.
They all use all of the elements, though.
Well, if that's the case, then fine. This looks much better. Okay, let's try. Let's go to the test program and change the new to 0 and see what happens.
Uh, Test. Actually, example.
I don't know which one
This
we're running here.
is. Let's check main. It's factorial. Okay.
Man, no. Let's not do that. Let's do this with the plus. Let's change the plus program. That's gonna be way easier to make it work. Okay, now let's change the main.ml and try to run the program and see the compiler telling us what's wrong.
Plus.
What's wrong, compiler? Okay, the register allocator is mad. Line 72. And by the way, I am 100% stealing this way of doing compilers from Zozin. Like he was the one that introduced this to me. That when you're adding a new feature to the compiler, you just do the minimum amount of work until it becomes happy.
Okay.
Okay, so 72. So
Oh,
it's
it's because
neither.
this is incomplete. Yeah, this is incomplete now.
Yeah, so we need to do something about it. What should we do? This is
We
register
need.
allocation.
We need. Actually, this is backwards. This is completely backwards, Lemos. We need to actually do something else first. We need to. Because, like, we have integers in the AST, right?
Yeah.
But we actually don't have integers in the machine level. We need to add integers to the runtime as well.
I would. Well, we would do that anyway. That's code generation, right?
No, it's actually it's either the machine or the evaluator.
No, it's definitely the machine. Definitely the machine. But that would be a code generation problem. So I would just keep going with the flow.
No. It's not really just code generation. It's also evaluation is going to break as well, I guess.
Yeah, but evaluation is the last step. We can do this out of order if you want. It's just because I would like to go with what is the compiler immediately telling us.
I mean, the problem is we're going to say, okay, in order to handle an integer, we need to allocate integer. This can go away,
Can you
but this
change the
function
F to
doesn't
an I?
an f to an I.
Thank you very much,
We
sir.
allocate integer, but this doesn't exist, which means we need to implement it, right? So we do.
Yeah, just
This will
copy the
probably be
allocate. Yeah,
yeah, this will be recursive, right?
yeah, it's just gonna be like the other ones we have below.
Allocate integer takes
An int takes an int,
takes an int,
a t, a term
takes a
q, and a
t,
t,
takes a term q,
returns a t.
and returns t.
Yeah. Yeah, I would just copy paste whatever we have for functor there and change it accordingly.
We're gonna need to do this is a function. Takes an I, takes an allocator, and takes some terms.
And it returns something. So the first thing that
Hmm,
we do is to call allocate recursively in the case of the functor.
yeah, no, that's irrelevant because integers don't have nested information.
Yeah. So we just call terms. We just do the terms.
No, we need to do.
Yeah, no, we don't do the terms. That's right.
Allocate variable. This is wait. This is the register allocator, right?
Yeah, we're allocating registers in here.
We don't need to allocate a register for an integer.
Well, if that's the case, we need to do
Do
something on
we?
line 76. Actually, I don't think it makes sense to allocate a register for a number because that's not like something we have to remember later, right? This is not like a variable.
Well, a number will always be either inside of an argument to a predicate, or it will be nested as an argument in a functor, which is an argument to another
Wait,
functor or a
wait.
predicate.
Maybe we do need to register allocate numbers because we need to remember where they are to unify.
We don't. A number is just a constant.
Do we have any conception of constants already in the compiler? I don't
The
remember.
closest, the closest thing we have is functors with arity 0.
Hmm. Yeah, but those are functors. I don't see them as a constant anyway, just because they happen to be 0. Uh, okay, so that's the question. Do we need to allocate register for numbers? That's the question.
I don't think that we do, no.
Well, in that case, don't put a catch-all there. Just call allocate loop.
Oops.
Yeah.
If it's an integer, we just recurse.
We just recurse. Continue execution. Yeah,
Yep.
this is the problem. This is the problem. Something broken in the code generation that definitely should tell us where, and it's not telling us where. This is a problem for compiler development. Uh, okay, now we need to discover where in the code gen we are failing, which is always fun.
Mm,
Go to the code gen and search for finds.
I think I know the problem. The problem is we are not allocating a register for an integer, right?
Yeah,
But elsewhere in the compiler, we're presuming that everything has a register associated with it, which is not the case anymore.
that makes sense. That makes sense. So we need to discover which places we need to undo that assumption.
It's everywhere.
Not everywhere. There are not. There are not. There is a finite amount of finds in the code generation.
Hmm. Yeah, this is not quite gonna work um, if we don't do get structure, put structure, get variable, put variable. I wanna die. We're gonna need another set of these for like integers. Or rather, we need to add integers to this set.
Wait, we're gonna have to have integers to this set.
Because like we have get structure and put structure, right? We have
Can't
get
we
variable and
just can't we
put
just
variable.
upgrade the register type to be something else?
No, we can't.
That doesn't make sense. You're telling me that you cannot go to the line 2 and then another tagged union there, which is just
No,
gonna be a
no,
number.
we can't, Lemos.
I don't follow. I don't follow at all. Why we can't? Why can't we?
Okay, we have permanent registers, which are called Y registers, and we have temporaries, which are X registers. What would adding a Z here accomplish?
Well, because now everywhere that we're using registers and assuming X or Y, the pattern match is gonna be non-exhaustive, and we can go there and treat the integer case.
But then integers don't really behave like normal values.
Yeah, that's why we have to treat them differently.
But they are normal values, Lemos.
I don't see the problem. I'm sorry. We have instructions that receive registers. We want the same instructions to be able to also handle numbers. I
Which means
don't.
we need instructions that put numbers in registers.
But if we're gonna do that anyway, why don't go to the register allocator and just make allocate a register for a number?
Because we already have registers, Lemos.
I'm so confused, man. I'm trying to backtrack a little bit. So we just settled 5 minutes ago that in the register allocator we're not gonna allocate register for numbers.
We won't, no.
Okay. But we want get structure, put variable, get variable. We want those same operations that right now are exclusive to registers to also handle constants. Maybe in the future also strings, why not?
Yeah, we need to add get, I guess, get number and put number. Although
No, that's not. I don't see why that's the best option. Why are we gonna do all the copy pasted versions of these functions if they behave the same aside from the inner contents of the thing? I
um,
must be missing something in here.
I suppose we could have something like get constant and put constant, and then they work on both functors and
That's what the
integer.
book has.
It isn't actually.
Am I blind? I could have sworn that they actually have get constant, put const.
They do, but these are not general constants. Those are just specialized versions of well, they're basically just arity zero atoms or functors, I guess.
Really?
Yeah, this is not really introducing numbers. It's just saying, okay, if you have a functor with no arguments, actually you don't really need to allocate space for that.
Yeah, I really gotta go to that page. So this page is 63. Uh,
Yeah, this is the section, right?
Heap space for constants can also be saved when loading a register with or binding a variable to a constant. Rather than systematically occupying a heap cell to reference, a constant can be simply assigned as a literal value. Yeah, man. Maybe I need to read more, but it's not talking about what you were talking about. I think these are constants.
Hmm.
Let me read more. Uh,
I suppose we could eventually extend this. Well, if we were doing following the book and then looking to extend the model, I guess we would probably put integers here. So yeah, we need these instructions basically.
yeah,
We
constants
don't.
and lists. Yeah, he is treating constants and lists as separate things.
A list is not really the same as a constant, though.
That's why he's making the separation. Makes sense. Oh, okay. Actually, he does say we introduce special instructions for specific handling of zero arity structures, aka constants. So zero arity structures. Well, what are we gonna do? Are we gonna represent numbers or zero arity structures?
We could, but that sounds painful.
What about my other idea about upgrading the arguments of all the gets and the puts in the code to
That's a
not be.
no-go, Lemos.
I don't understand why. Could you elaborate? I have no idea why you're saying that.
Does your CPU have separate registers for each type of value that it handles?
Well, no, but you're not
Like,
implementing a language for a CPU. This is a VM.
which is inspired by a CPU.
Well, I agree that it is inspired by a CPU. Inspired being the key word there.
It's intended to be used to compile to a CPU as well. So, you know.
Okay, so we're gonna make the design potentially worse just because we want to mimic the idea that this will eventually be a CPU running it.
Don't you want to eventually compile to machine code, Lemus?
Well, I do that. I do want that. And I understand that having simpler instructions on our VM will probably make it easier to compile to machine code in the future. But duplicating everything that is using register to use something else just because of that?
It's not duplicating. We need to add basically this set of instructions, essentially.
No, but that set of instructions is being suggested if we interpret constants as zero-arity structures.
They should work for numbers as well, though. Actually, they should work for any kind of immediate value. But if we're going to use, well, if you allow me to use the terminology from Lisp compiler literature.
Well, if that's the case, let's just implement that.
Okay. Get, put, set, and unify. Get, put, set, and unify.
Yeah,
These are out of
copy from
order.
line. Well, I was about
These
to
were out of
suggest an
order.
easier copy paste for you, but okay.
So value will become constant.
And we receive, instead of receiving register.
We need to receive a constant. We need to
Yeah,
receive a
let's go one by
constant,
one.
which
So you want to start
is
from set, right? The set only receives a number. Well, constant. Let's make this a type, constant.
um hmm. I think I think hmm. Oh right, because this has a separate tag from okay, that makes sense actually. Um sure, let's do that. Constant of
No. I'm talking
and
about making a constant type. So type constant equals. And then in the future we can extend for other types of numbers and stuff like that.
constant equals
Right now, only
um
integer. But in the future, we're gonna make this more stuff, do more stuff. Yeah. So line 15. It's not register. It's constant,
no, it takes both actually.
not set constant.
Oh yeah, not set constant. That's right. This takes a constant.
Get constant and put constant. The first arguments they receive constant.
Mm,
And unify constant also receives a constant. Yeah, that's pretty much it. That's pretty much it. Okay, so how does the code generation? Well, we have also implementation, but do you want to go to the evaluation now, or do you want to go to the code generation?
uh, that's a good question. Yeah, this is
Yeah, no, this will
terrible.
fail. Yeah, that's terrible. So we need to discover where we need to introduce that.
Where we need to introduce that? Yeah. Um, let's see.
No, it's code generator, and we need to keep adding prints all day there.
Let's
So
see. Actually,
let's try
we
to not be dumb.
no, no,
Let's
no,
go
no,
from the
no. We
top.
can. Yeah, we can start from here, right? Because
Yeah,
this takes an AST.
yeah, this is the beginning. So where are we gonna fail first? We're doing plus. So this is not query. So let's jump query altogether. we start by doing the declaration of plus. And plus has multi-declaration, so it's 385 onwards for sure. And then we do the split last, and then we do, yeah, generate declaration and patch. That's the first one.
I think that's the only one that's gonna break here, actually.
Yeah, we only use this one. We use it 3 times. So let's go there.
Argument emit is going to break eventually as well. I think that's where we're going to eventually end up, actually.
So then we call all of these things. Okay, this we have only one place to go here, which is generate single declaration. Nice. So we're not gonna go to 331. We're gonna go to 341 because this plus has a body. And then we're gonna go to emit head and emit body. Those are the 2 places.
Yeah, I think we bottom out on emit argument eventually.
So then we have emit on argument. Yeah, go there, which does all of these things. And maybe it's line 171 that is not matching there. Or actually 158. 158 maybe. 158. Put a print before 158.
Either a variable or a functor. Either a variable or a functor.
158. This is not a lazy language.
Oh right, the find is breaking, that's true. Raw register, find lm registers. And then arg register. You know, the problem is that this is actually not needed in the constant case.
Yeah, that's
actually.
well, exactly. Let's first confirm this is the place that is breaking, and then we're gonna have to think about that what you just said. Add the print. I'm gonna try to find how you do lazy stuff in
No,
OCaml.
it must be. It must be.
No, this is not. I think there's a better way of adding like closures lazy or stuff. Laziness OCaml. So how do you do lazy stuff in OCaml?
How do you do? Oh, this is not needed. Actually.
Lazy keyword, is that it? Are you joking? That's it. And then you do what? Lazy.force or whatever? I guess.
Lazy.force.
Yeah. Okay, so that's it, man. That's it. Just go back, Control Z all the way until you have the raw register on the top and put lazy there. Done.
The problem is that this doesn't work because of this. We need to put the lazy here as well, and then I suppose we can force it down here.
Yeah, I just don't like the copy pasting because, well, I don't like the copy pasting.
Well, this is reducing the scope of those variables. I think that's generally a good thing.
Okay, so there is a lazy keyword apparently.
In fact, we don't use register up here at all.
Yeah, register can go. Register 159.
We use raw register here, here, and here though. Oh, we do use it in 2 places, I guess.
Yeah, but are those 2 places? Yeah, they are separate, in separate branches of the pattern matching. Yeah, so let's add lazy there and see what happens.
Like this?
I'm not completely sure. I'm trying to find more examples. Man, the docs here, they don't have a single fucking example. OCaml people. Okay, AI is giving me the thing. Yeah, it's exactly as what my Nathan said. So it's lazy with parentheses, apparently.
You mean like this?
Yeah, and then you use lazy.for, lazy with capital like module.
You mean like this?
Yeah, yeah, you do it like that. But I have a question. What if you have a lazy thing and you have another thing that depends on the lazy thing, but is also lazy? Do you need to force and then re-lazify it?
You do.
That's kind of
Why would you
trash.
not?
Well,
No, it's exactly what Haskell does implicitly.
well, because it could do this for us if we say that something is lazy, but it depends on something else that is lazy. That would be kind of poggers.
Idris does something kind of like that, except it's actually type driven.
Yeah, apparently the
String
lazy
registers.
module doesn't
Why
have such
is
functionality.
this? It has this type, but it was expecting something
Yeah,
lazy
once
apparently.
174 is fucked. You need to put force in there. I'm almost making a separate let just for this nonsense. You're gonna have to do that everywhere, man. Let's do it like this. Let's do a let before 173 that is the real raw register, like without fucking already forced, let's say. And you can do shadowing in this case. This is actually a case that I'm okay with shadowing.
I guess we can do this as well, right?
Yeah. Yeah, and then you can get rid of the multiple forces that we just introduced.
Hmm.
And you need to do the same thing, the same kind of thing, yeah, down there. Nice. Nice, 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 nice. Okay, now we need to do a pattern matching on the LM, right? I believe.
Which we already are.
So constant in there. And
No,
for
it's an integer, actually.
actually you're right, you're right. Okay, what do we need to generate code for this guy? Let instruction.
Uh,
It's definitely a let instruction. And then we make the put or the get or the set or the unify constant versions.
variable value func.
Const.
Um, yeah,
Is const taken?
const.
Oh, it's not. Fuck, that's nice.
Okay, this is mildly annoying. We need to add a layer of parentheses here.
Yeah, I will fix this. There is a PPX that does this bullshit of the tags being the constructors being constants. There is a PPX that does this. Somebody just needs to do it. Okay, we need to be careful though. Sometime you missed the parentheses, my man.
No, I didn't.
You did because on oh actually you did both without parentheses, so it's consistent, so it's fine.
It's what the formatter does. I did the first one with parentheses because I just copy pasted so it was easier.
Okay, but we need to be careful. We need to see if should those two guys be puts and gets as well for constants.
They should, because this is where we're initializing the registers. And put and get, they both take an extra argument for the register you are initializing. And this is necessary because this is an argument register, right? We're preparing a call, essentially.
Cool, 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 cool. Okay, so let's do let instruction inside the 174. Let's create the instruction that we're gonna put into the memory.
Let's see, we don't need any of these. We don't need to update the scene registers, do we, though?
There's a problem. I think put constant and get constant they need to receive registers.
We have a register, though.
Do we? Are you sure?
It's the argument register, Lemos.
Ah, I see. So let's do it. What are we waiting for?
Uh, this is a thingy of registers, right?
Yes.
add the raw register, otherwise we just keep it. Yeah, I guess we don't need to do any of these, to
I
be
also
honest.
don't think we should need to do any of that.
That means we also don't need this, which means
It's
we
just literally
need
pipes. It's just a bunch of pipes.
to do add instruction and then put the allocator.
That's it. And it doesn't
And this
even
is
need lets actually. You can just do like a single series of pipes.
okay, so generator and store
Pipe.
goes to
Add instruction.
add
And now we
instruction
need to create the instruction in line here.
const integer int, and we need the arg
Arg.
register.
Arg register. And then we need to do the put allocator. Why is the formatting not fixing this shit?
Put allocator because it's
Yeah.
manual lemons.
I think you need to do cell.integer there in 176.
Oh, right.
I'm not sure.
Mm.
I'm actually not sure.
Oh no, it's actually this is gonna suck. It's actually cell.constant
Ooh, I
of
see, I see. And then cell.integer.
cell.integer of int,
Wait, but
right?
it's still red as fuck. Something's wrong.
Mm,
Oh, you don't need the extra layer. That's it. Just
I
remove the...
I don't need the extra. What do you mean?
Yeah, you don't need the cell.constant, essentially. That's what the type was saying.
Oh, actually no. The problem is this, in fact.
I still don't think
Yeah,
so.
no. Yeah, no. I still am missing.
I still think you don't need the cell.constant. I will die on that one.
Okay, let's
Yep,
see.
yep, don't need that. That should be enough. You're missing parentheses now.
Not anymore.
I still think you're missing parentheses, friend.
Where? Oh, I need the allocator actually. Of course.
No, no. This is some
Mm,
silly type problem. Let's go to the type of put constant again. Go to the put constant, man. Let's see the types.
This expression has type A and B, but we needed a cell instruction. Oh, it's because we need to do cell dot
Constant.
wait, no, cell const should return an instruction already. Why isn't it?
That's why I want to go to the types of put constant and get constant.
Variable value func const, and we're using const here. Takes a constant and a register.
Now,
Oh,
const takes a tuple. That's what I said about your missing parentheses. There we go. There we go. Now we're talking.
yeah, the close paren was here. It needs to be down here at the end.
Yeah, so that's it. We just made integers. So let's try to run this. Let's see if do we break. Oh,
Um,
we're not gonna know. That's cool.
yeah.
Okay, so I would recommend for us to put some sort of print in the evaluator to know when we got out of the code generation.
It's not. It's probably not the evaluator that's breaking though.
Yeah, no, but we should make sure.
Find opt. Actually,
Yeah,
if I
just
just
grab
grab
for
for
finds.
find,
Yeah,
yeah,
just grab for
that's
finds.
find opt, find. But this is for X registers, so that's probably fine.
And these are in the evaluator. Code generation is below.
Those are for pre-register. Raw register in here.
Emit argument in queue nested if not in queue. These names, man. These fucking names.
Yeah, we need to handle integers here as well, actually.
Well, but this one is a little bit more complicated because you're doing the sing registers find opt thingy outside of the pattern matching. So let me think a little bit.
Variable value. This is... Yeah, we need another argument here, actually.
Yeah. Const. Yeah, but think in the positive sense. When we do this, we're gonna have support for any constants anyway. Well, constants that don't have
Const.
special semantics.
This is going to take a constant, actually,
Yeah.
right?
Yeah. I'm trying to figure out how we're gonna get rid of how we're gonna get around line 67.
What do you mean?
These will not make sense when we start adding the lazy to line 65 and 66. This find opt thing. Again, this is not a lazy language, which means this find opt is not gonna fly. The find opt is not gonna fly. Tragic.
Hmm.
Yeah, that's tough. We have the only option that I can think of is to grab 67 all the way to 71 and put inside the individual branches from now on. I don't know how we're gonna get around this one.
One moment. Seeing registers. Emit arguments in queue nested if not in query.
What a name.
This raw register is being used here, here, and here. Which means it's actually only used for the find opt. The
Well, so
register
wait, go back a little bit. So we can move
is...
it. We can move 60. But we need the raw to make the known raw, and the known raw is being used somewhere else. Fuck.
The register is used here. The instruction is used in both branches.
Man, that actually sucks ass. The only other case we're not using we could put raw register and register inside the 67, but we can't because of the fucking 77. Go fuck yourself.
No, we can. We can
We
do...
can't because of the 77.
Look, this is lazy, right?
Yeah, yeah.
This needs to be lazy.
That okay. I want to see which trick you're gonna use. Let's see.
I just have to not pattern match Lemus.
Not pattern match. No, that's not gonna fly because line 68 is not matching now.
No, it works. We just need to do new sing and inst. And this is lazy. But actually,
Wait,
and this is a little
is that
bit of a
gonna work?
problem. Why wouldn't it?
Because the find opt type is fucked.
Lazy.force.
It does work. Damn. Okay, so the find opt
Uh,
doesn't care if it's lazy.
this needs to be forced.
We're gonna have to do that many times. Just make a let, man, inside the lazy.
Let. Yeah, no, actually. Yeah, we can do this actually.
Nathan is poking me. For what you guys are using lazy, by the way? to, well, we are using the lazy to not have to duplicate code. That's what we're using it for. No, I don't mean evaluating twice. I mean that there are pattern matches in which most of them require something, but one of them don't, and we don't want to copy to all the individual pattern matches the ones that need it. So we're adding lazing and forcing inside of it, inside of the matches. Okay, so what did Marinho do here? So now register and raw register are lazy. Uh, we have a problem though. Line 79. You also need to force
7
the register.
new sing and inst in.
Yeah, line grab line 68 and put it inside the variable matching as well. We need parentheses in there probably. Yeah. Thank you. Grab line 70, and we also need that inside of each in the pattern matching there. Yeah, that's what I'm talking about. No. You need to
Uh,
paste it. You need to paste it.
no, this can just be a lazy.force.
No, that also works. You need to do 77 again on, yeah, there. There we go. Okay, this is not the worst. This is not the worst. It feels like a controversial decision, but I'm fine with that. So now let's match on the integer on 75.
Why would this be controversial though?
Because I have a feeling that most people would just duplicate the code instead of doing what we're doing right now. Integer. Okay, so what do we need to do in here?
Uh,
Same thing?
Same thing actually. Let's see. Oh, I have a bunch of stuff that's not committed. That's annoying. Where? Here.
No, if I actually never did any serious programming with lazy. Uh, like in a language that doesn't have supported like in from scratch like Haskell. So I don't know how this is gonna go. So I'm excited to see what's broken.
Uh,
That's broken. Okay. Okay, that's cool. That's actually cool. No, I actually man, that symbol is tough. That symbol is fucking tough. But okay, it is what it is. Okay, what else? What else? Try to run the program. Let's see if we go further.
1 second. Let's see if I'm still. Oh, actually, this is not gonna type check at all. Yeah, because I just added a new argument to this thing, and we
Well,
need
but now
to.
the colors are broken, so let's go there.
Okay, the first one is
Nathan,
on line 145.
Nathan is also suggesting that we could mimic the laziness by wrapping it in a lambda.
We could, but that would not memorize it.
Damn! Get wrecked. Oh, this is where we do sets versus unifies. Okay, so do you know which one is which in this case?
It's just set constant and unify constant, I guess.
Well, we only have two
V
remaining ones,
cell
so
dot set constant v. Oops. And this is
unify constant.
unify constant.
Damn. Well, but we are missing the constant in here, right? Yeah, on this match on 120. Do we need it in here? This is a mid single field argument.
We do.
Okay.
I,
So what else? Oh, but in this case, the map, the find opt is inclusive for only two variables. That makes our lives easier. But I have, yeah, raw register and register problem. Just put lazy on those, and then we can do the same trick that we did the first time. Yeah, lazy is a keyword, it's not a function, apparently. So sad.
well, it can't be a function, unfortunately. I mean, it could if it took a lambda, actually, but it doesn't.
Yeah. Well, there is actually a version that takes a lambda, if you want to know. Which is called from fun.
How fun.
Which is slightly more efficient according to the docs.
Slightly more. Shouldn't this sugar into that? Why would that be more efficient?
It's saying that the from fun is advanced.
Why?
That I have no idea. But it is saying here that it is more advanced.
Let thing equals lazy dot force thing in. There.
Yep. But we also
And we
need the
actually,
register. Yeah, we also need it in here.
yeah, we need this here as well.
Damn. Okay. Integer time. Man, this is actually going pretty smoothly, or everything considered. Like, assuming that this is all we have to do, and now it's just a matter of evaluating the shit. Damn. I'm actually impressed. Okay, what else is broken? Compile, compile, compiler, tell me. What is wrong? Emit argument in Q nested if not queries caller is now fucked. So 230 something. Yeah, there we go. So this is missing a new argument, which is probably a lambda. So are we gonna bet it's set constant?
It must be.
I like your confidence, Maria. I really like it. Compiler, tell me more. Oh, there's another one. Compiler, tell me more. That was weird. The register
Line.
allocator is fucked now.
The
That
register
is
allocator.
unexpected. Could you go there?
Line 92.
I'm actually a little bit
Oh,
surprised.
no, actually this makes sense. This makes perfect sense.
Oh, but why did the compiler not tell us this before? Ah, I know. It's because... No. This is constant, not integer.
No, it is integer.
Are you sure?
Yes, I do. I am sure. There.
Yeah, so I don't understand. Why the compiler didn't tell us this one before? Damn! Okay, so apparently we managed to get along with the code generator and the register allocator and the parser. And now it's just a matter of eval.
Evaluator.
Let's go to the implementations in the book.
Ah, we need to implement 4 instructions, right?
They are not hard though. They're not hard.
And we need to implement unification for constants now
They are
as
all,
well.
that's also not hard, according to this thing. Okay, so let's start with put constant, which is one line only.
Put constant. Okay.
Just scroll down.
Oh, okay, that's easy enough.
Yeah, no, this is fine. You made it sound like it would like a very non-trivial endeavor.
Let's put them here, I guess. Let's put constant
You're gonna receive two things: a constant and a integer, a register. Sorry.
cell constant, right?
Yeah. And you need to receive a register.
This is machine dot register, right?
I don't
No.
remember anymore. Scroll up to first to see examples. I have no idea.
Oh, this is the evaluator. It should be just register in this case, right?
I have no idea. It's
No, it's cell dot
cell.register.
register.
Let's
Okay.
see. And I have another thing. I think we can extract the constant. We don't you don't need to do what you did there.
Extract the constant.
Yeah, because in cell.constant can contain yeah. Okay, now we're talking. And you need a computer.
Um, we need computer, which is machine.t, and this returns a new
Yeah,
computer
yeah.
and a boolean. No, just a new computer.
Just computer. Okay, let's go. Um,
Hmm.
so what is saying we need to create a thing. I already forgot how to do that. So let's put let constant and constant like put extenso, And let's create a cell. Let's create a
Uh,
cell.
yeah, we need to do something like we have a set register, right?
We have set register.
This takes a register, which we have. This takes a cell, which you can build trivially,
And a computer probably.
and the computer. Okay, so this is just set register,
Heg
cell
cell dot
dot
constant
constant
c.
c computer. There we go.
Damn. How elegant. Next one, get constant. Copy the type signature. Yeah. This one is a little bit more involved. So the first thing we need to do is to do a deref on the value of the register, which is a little weird because we don't do this operation, right? Ever. So
We
is it?
could if the register has a variable that could be a constant, you
Are
know.
we gonna do a lookup first and then do the
We have to
deref?
we have to do a yeah, we have to do a cell deref here actually.
No, but we need to do a lookup first, right? We need to go to the register map and do a lookup on the register.
We do actually.
Yeah, this notation is weird. Okay, so what is the name of the register map? I forgot. We need to
Actually, I
extract
think
that from the
get
computer.
variable does something similar, right?
Uh,
Okay, this does a get register apparently.
Actually, that's it. This returns a cell. That's it. Just do a get register. And then we deref the cell out of it.
Okay, let
ADDR.
addr.
Yeah,
It's not an address, Lemos.
it will be. Believe me. No, 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 no. ADDR.
Um, let register value equals
No, we're gonna do the both
get
operations combined, my friend. You are slow.
get register reg machine is the computer.
And then we do at on that to deref cell. Done.
Mm, deref cell, and this also takes oh, this takes a store actually.
Yeah, so just wrap in parentheses, it's better. Get
Uh,
register doesn't write into the computer, right?
no,
Yeah. ADDR.
it's not an address, Lemos.
It's
Or
written.
it shouldn't be an address actually.
It's written as it is.
No, but it's doing the case on the store of the address, right?
Well, yes, but I would call this a DDR anyway. But okay.
No, no, no. I'm using dref cell, not dref lemos.
But isn't the ref cell? Oh, we changed
Oh,
this.
actually, oh, we can just do constant.
Welcome to OCaml. Uh, yeah, I don't remember anymore the difference between. Wait a moment.
That
Ah,
that is basically this lemos.
no,
The
no,
this.
I believe you, but what is the difference between the ref and the ref cell? That's kind of.
I was kind of tired of having to do this whole. Okay, if it's a reference, we have to do a lookup, but then we need to check if the thing is a functor, which means we need to change it to a structure. Otherwise, we return the thing. Yeah, this was bothersome. So
Okay, but this is different semantics anyway. Okay, so do a pattern match on the result of that thing. Go back to the get constant, I guess.
if it's a reference, we need to bind it. If it's a constant and they are different, we fail. Otherwise,
We fail.
fail.
Yeah, this is pretty easy
Okay.
to put in the code.
Get constant.
Man, this is gonna be pretty easy if it turns out that's it. This is gonna be the most successful session in years. We don't need the value of this, so just do a match on the entire thing.
Match with.
Yeah, so if it's let's start with being a reference, I guess. If it's a reference, we ignore the value.
Actually, if it's a constant with
Why we're not
C
the
prime,
reference goes first, man.
computer, because this is easier actually to implement. Computer with fail equals
C,
C not equals
is
to
that how
C
you do
prime.
that in OCaml?
Well, LSP is not complaining.
Okay. Uh,
Otherwise, reference, this is to do. Otherwise,
we
we
always fail.
fail.
Yeah.
Okay, the reference case is
Oh, wait. There is an operator to the lazy.force. Exclamation mark, exclamation mark.
double exclam.
So
Wow.
that's the forcing. Okay, that can make some pieces of code a little bit neater. But I could not find the difference in OCaml. Oh, it's not that. It is the smaller than, greater than shit. Oh, this is a structural equality against physical equality. So the exclamation mark equal is physical equality.
So this needs to be double equals then.
No. We need to do. Do you want structural equality?
We do, yes.
So it's less than, greater than. Yeah. According to AI, of course. Um, okay, so the reference. Let's go to the reference. So in the reference, we need to put stuff in the store. So it's gonna be
Uh,
store dot yeah uh,
um,
put, just put, and then I don't remember the type signature of this thing. Okay, so we first
takes a
put the
value,
value and
takes
then the
an
address.
address. Okay, the value is
Open close parens, and then addr computer.
cell dot constant C. The address is the address of the reference.
And probably comes a store now. Computer.store. And now we need to trail it, probably. This returns a new store. This returns a new store.
This goes here, but then
We need to trail. So I'm worried that the trail definition, yeah, the trail function is not. Uh, oh, actually, it is up here. Oh, so it's fine.
Trail takes an address
And a
and takes
computer.
a computer.
Yeah, just pipe the new computer to trail and put the ADDR as argument. There we go. That's it. Okay, that's it for get constant actually. Let's make set constant really, really fast style here.
Takes the constant, puts it on the heap, bumps the age
Each
register.
register.
Okay,
Done.
seems easy enough.
Yeah, but this doesn't receive the register, by the way. This receives only the constant.
Uh,
And don't forget to
this needs
change to
to
set
be.
constant instead of put constant.
We need the age register.
Yeah, there is something fucked with the
Underscore.
parentheses. No, there is something fucked with the parentheses there, I think. Is that it? No, that's correct. Yeah, that's correct. Nice.
Then we do
Store dot heap put.
store dot. Let's grab the store from here as well, actually, since we're all destructuring it anyways. Heap
Heap
put
put.
cell dot constant c in
Age
the age
register.
register.
And all of these in a computer with store equals.
Computer with
Store equals this.
store equals this thing.
And don't forget to
Actually, you are
bump the
correct.
H register plus 1.
We don't need a pipe then.
Yeah.
Age register equals age register plus 1.
Probably it's because... Oh, you forgot an
Oh,
argument on heap
I'm
put.
missing the I'm missing the store here.
And you need to rename put constant to set constant as well. Yeah, it is something fucked with the parentheses. I figured that much. So the closing braces is not in there. It is immediately after the underscore.
Hmm. There.
Okay, last one. Unify constant. Should be easy enough. Which is essentially a combination. Yeah, can't we just call set constant in unify constant? Why not? Come on.
Wait.
That should be
Okay,
doable.
store of. This is basically get constant, right?
No, this is a combination of get constant and set constant.
Yeah, I mean the read. Okay, yeah, no, we can totally do that.
Yeah, easy. Easy, easy, easy.
Let unify constant.
Receives a
It
C.
just takes the constant, right?
Yeah, it's the same type signature set constant, essentially. But you need to grab H register. Actually, let's not call.
We
Let's
need
just.
the we need
Yeah,
the mode, right?
yeah, we just need the mode. Because we're gonna call the other instructions anyway. So now you do a match on the mode. If it's the read mode,
If
we
it's
need to do.
read,
Yeah, I don't know about
get constant, but get
S
constant,
register. You need the S register.
we need the S register.
Man, that's so cool. Why didn't he implement it like that?
We need the S register. That means actually,
Oh, you're gonna have to create a register, like a real register out of the S register.
this zeref cell can't be here, unfortunately. Or rather,
We
can I
just
get
don't use
away
it.
with?
We just don't use it. Well, like I said, you can lie it. We can lie to it, and upgrade the S register to be a real register, and then dref cell can do its thing.
That's not the purpose of zeref cell, though.
I agree, but we can
No, no, no,
cheat.
no, that's not what I mean. What I mean is S register contains an integer, right? An address.
Yeah.
Deref cell is when you say, okay, I have a cell. It might be a reference. I want to dereference it until I get something that's not a reference, or I get a free reference, essentially.
Yeah.
It's from cell to cell, not from address to whatever.
I see what you're saying. That sucks.
Well, write mode is easy,
Yeah, it's literally set constant. Done. How pretty.
but then get constant, we don't have a register, is the problem. Is the problem.
Man, it would be so nice if you could cheat the S register into a register that the ref cell can use its thing.
Hmm,
That would be very poggers.
I guess we can. This is essentially only using the register here, right?
Yeah, pretty much.
We can make a helper actually that does um,
Everything else. That does the pattern
get
matching.
constant from address. This is going to take, well, this. This is actually going to be not a register, but an address.
So this needs to be an integer then.
This needs to be an integer, yes. It needs to be an actual integer. And this
Computer
is going
and
to
return a
take a
computer.
computer.
And return a new computer. There we go.
But then match, we need to do store dot get from the computer dot store, and the address is this. This is the correct order, right? It
No,
isn't.
of course not.
With hmm,
Yeah, the body, all of these things. There we go.
okay, but
Man, can you remove the extra spacing on 48? Oh, thank you for matter. Okay, so now how can we do the thing? Reuse it down here.
actually, I have an idea. What if instead of taking an address,
We should just do the pattern matching and extract that to a separate function.
no, 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 no. What if instead of taking an address, we take a cell?
Which is gonna basically extract the pattern matching. That's what I said. Yeah, this is essentially the extracting the common parts. And now we can use it.
From
Jesus fuck.
the reference cell, then get constant is just going to be
Oh, that sucks a little bit.
C, and then we need the
Done.
cell,
Remove.
we need the constant, we need the cell, and we need the computer actually,
Yeah, but now everything
and
can go
everything
away.
else.
Done.
Oops. Yeah.
Bye. Yeah, so extracting just the pattern matching. That was the best way. Okay, let's do the same down there. Unify constant.
Okay. This is going to be get constant
From
from
the
the
ref
dereference
cell,
cell. Taking the
C,
C, the cell is going to be
deref of S register.
deref
Whoa, actually,
of
not that's not true. It's a store get on the deref. That's nasty, but okay.
What am I doing? We have the computer being the structure here. Store
S
as
register.
register. Get store as register. And then we need the computer.
Not S register. The ref of the S register.
Deref of the S register, but S register is an address already.
So?
I suppose we can do deref cell here.
But that man, if that was the case, we wouldn't have to do the thing. Oh no, we would have because we need the raw thing in there. Okay, whatever. Done. Let's go to evolve step and add those instructions to the big pattern matching.
Okay. Okay, so let's put it down here, I guess. Set constant.
You're gonna have a constant, and then you just copy the boilerplate.
This false is for halting, right?
Yeah, this is for halting. Don't forget to do the p register +1.
This is not unified value though. This is actually set constant computer.
Unify.
This is get constant, but this takes a constant and a register, right?
Yeah. Cool. Next. You set and well, not set actually. Unify and put.
This one just takes a constant. And there's no register.
I'm scared because that's pretty much. Damn! Printing failed. Man, I love compiler assisted refactoring. Fuck everything else.
Actually, if this is a constant, we
We need to
this
pattern match
return this.
again. Pattern match on the const. Now we grab the integer. And in the future, this is gonna extend. Maybe now even. If we make this work in like 5 minutes, why not rationals now? Fuck. I'm scared.
It works.
Jesus, man. I can't believe it. We set our goal for today, and we actually made it today. Jesus, man.
It
Okay.
works.
Format. Let's format the code and do commit. Why not? Incredible. Incredible. And these, my friends, is what is called compiler assisted refactoring. You just
Well,
change.
it's not technically a refactoring because we're adding a new feature.
Yeah, but in this particular case, adding a new feature, it is like we make an example, right? We make an example and we say compiler, let us know why you're mad, and we keep following the errors, we keep following the traces of errors. In our case, differently than Zosing, our error messages on the finds were trash. So that's why it was not perfect. But aside from that, every portion was like, I'm failing here, we go there and fix it. I'm failing here, we go there and fix it. All because we have the pipeline fully done. So this is the power. This is the power of this type of stuff.
Okay, we have integer constants. Now
We have two options. We either add more constants or we add special operation constants.
we should probably add some integer primitives because right now we can match integers for equality, but we can't really do much with them, right?
Yeah, I agree. Okay, so what which primitive is quick and dirty?
Which primitive? Can we do? I kind of don't wanna get rid of the plus example though, because like if we add addition, what's the point of this, right?
Well, this is an exemplification of the piano arithmetic in Karuta. This is a completely separate thing.
Um, Actually, there is one thing we can do that's fairly easy. You know this?
Yeah.
Yeah, this generates integers, but it's also a type check, right? We should add an integer primitive that succeeds if its argument is an integer and fails otherwise.
How do you write that?
Kind of like this. Let's see. We need machine. Is it here? It is actually. Is integer of register of register. Should it
Man,
be of register?
I really wanted to have a thing because we see what's going on now. We are gonna start to add dedicated instructions for dedicated primitives, and they're gonna be all combined in a gigantic, ginormous instruction type. I wonder if OCaml has anything that allows us to like subdivide and then unify them later back. That would
Hmm.
be so useful. But okay, I'm just ranting right now. Okay, we're gonna actually add an operation that checks for integer.
This takes a register, right? Is that correct? It
Why do
should
we need a
be.
register?
Well, this is an instruction. It needs to operate on
Ah,
something, right?
oh, we're gonna pass an argument that's gonna be in a register somewhere, and then we need to know. Okay, are you an integer? I
Yeah.
see. I see. I see. I see. Is this the easiest one though? Are you sure about that?
Yes, because if we try to do this, actually that's gonna succeed
Of
because we're
course it
not.
will. Okay, no. We need. Are we gonna have special syntax for this check?
We probably should. Yeah, we probably should do something like if
Let's
we
create the
do
syntax.
int. No. It doesn't need to be special syntax. It can just be this. Like you know how we do the debug trick where we replace this with a primitive instruction, right?
We're gonna do the same thing.
We're gonna do the same thing. Yeah,
Okay,
like
I'm
this.
convinced. Let's go. That was actually a very good idea, Marie. Okay, where are we doing the hack for the debug? Let's
Uh,
start
bef-
from there.
Actually, before we do that, let me just do this. Uh, is integer is integer
Man, that's
of computer
yeah, but why are we doing this now?
because this is very easy.
Ah, man, you're still not following the philosophy. But okay.
Look, it's literally just is integer takes a register, which is
Cell.register
cell.register
computer.
takes the computer, which is a machine.t, returns a computer, and then all it needs to do is
Computer with fail equals.
oh yeah, actually, yeah, we need to do this as well, right?
Oh yeah. Well, not exactly that, but yeah. Yeah. There's something wrong.
P register plus 1. Oh, we're missing this, I guess.
Doesn't seem like it.
It's because the function is integer, it's
Ah,
not
yeah,
defined.
yeah.
That's
Actually,
a, that's a, yeah, that's a syntax error.
yeah, that makes sense.
Computer with fail equals
Get register.
match. Yeah, we need to get the register. We need to dereference it, and then we need to check if it's a constant, which is an integer.
Okay, so deref cell at
Let cell equals deref cell at
get register
get
register
register
computer
computer
in,
in
and then match that with,
match cell with
and then if it's a constant, and then we check if it's an integer, and then we check the. Actually, that's it, right? If it's in that, actually not even. You can go further. Just pattern match constant integer directly. That's it.
oh, this is fail, so this actually should be backwards.
You're probably missing cell dot something. Yeah. And in the constant as well.
In the constant as well, right.
What else it's complaining now?
This pattern should not be a constructor. The expected type is
Wait, what is the output of deref cell?
is a cell.
No,
Oh, right.
it's a function. Oh, you need to pass a store somewhere. Someone is missing a store.
Oh, actually, I see the problem.
No, the get register still needs either the computer or the store. I don't remember. Now we're talking.
That's it. That's literally it.
Okay, anxiety apart, let's go to the parser. Well, not the parser. Whatever is the place that we're doing the debug trick.
I think it's in the code gen actually.
We need to do a very similar trick.
Emit, actually, let's search for call. Actually, let's search for debug. That's probably better.
There we go.
Yeah, here. Here.
What? Okay, so just break this, add more matches. That's it.
Okay, if we're calling debug, we do a cell debug.
Yeah, just break the line after the with, and let's start adding more matches.
Okay, let's do that.
So there is one.
There's
Now,
the catch-all.
and then we're gonna go to the.
If
This
we
is
are
actually pretty
calling
convenient.
int of 1, we actually need to emit
Cell is integer.
Actually, do we even need to do that to take up the register? Because this will always be. I mean, I suppose. I suppose technically we can optimize later to not have to always check the first argument, but for now let's just do
But what's gonna be p register?
cell.register x
I don't think that's how you do that.
x0. Yeah, I don't think it is either. Cell.register.
I think it's cell.x.
It is actually. Yeah.
Is that
Yeah,
it?
for now. Yeah, it should be.
Let's go. Example time.
Okay, let's see.
Just go to the plus and swap the natural definition there.
Plus.
Yeah, that works.
Yeah, that should work.
Damn.
Pattern matching failed. 3 to
I'll
9
be back.
on the code generator, apparently. Ah, yeah, because that's a tail call. We hit the corner case. No. Ah. We hit the freaking corner case. Let's cheat for now. Let's call this EQ actually. EQ X0, I guess. And it's broken elsewhere. Interesting. 287.
I heard everything. Yeah. Okay. So we got corner cased. We got owned by our past selves.
Emit argument, emit body.
What the fuck is this?
Hmm.
Emit body. Oh, oh, wait. Okay, I see. I see. It's because the int call is actually in the body of something, right?
Emit match individual element, blah blah blah. Counter. What's the counter for?
But that's a little bit weird. Why? Why? Ah, we are
Because we're
emitting.
not.
Go on, go on.
Yeah, we're not handling constants here, and we have to.
Yeah, but why do we need to in this case? In this particular example, that's kind of weird.
It's because we were not
Ah,
actually.
you put it a number in the equality there. I see.
Well,
Yeah. Oh,
yes.
this is to get around the tail call problem. It is.
Yeah,
Is
this
it
to get
that
around.
hard to fix that right now?
Probably not, but we're almost out of time.
No, but if it's 10 extra minutes, man, fuck it.
Constant, const. If it's a constant, we need to. Actually, what am I doing? We already dealt with that, right?
Yeah, just search for constant in that file somewhere. You're gonna find. You're gonna find the
Actually,
thing.
this is not a. Actually, this is not a constant. This is an integer. In fact.
Yeah, that's also true. You probably already Oh, you didn't commit.
I was looking at the diff from the previous commit actually.
I see. It's still
Okay,
fucked.
what's wrong? What is wrong? Generator, allocator, store, and also counter +1.
Oh, so it's not put
So
allocator. Well, it is actually put allocator, but kind of. Ooh, that's gonna look terrible. Oh, okay, that works. But it's not const, apparently.
no, this should be put constant actually.
Okay. I'm glad you have that all of that in your head, Marie.
cell.putConstant, and of course this doesn't work with apply because why would it? That would make way too much sense.
Put constant requires a register, no?
Put constant, it requires a register as well, actually,
Which
which should
register are we gonna
be
use?
cell x counter.
Man, I have no clue how you have all of that in your head. Okay.
It's not in my head, it's here.
No, yeah, but in your head, the ability to make sense out of it. Okay, can we go to the to-do? Well, let's first see if this works, right? This should fix it.
Unreachable get value.
That's
Interesting.
fucked.
Oops. Oh,
What?
of course. Actually, this makes perfect sense, in
Wait,
fact.
why of course? I'm confused.
This is get value, which takes two addresses, but we're not handling the new constant case here.
How easy it is to fix that?
Okay, if it's a reference or a structure. Oh, this is using unify. This is using unify. Wait. Right, because we can
This
do a
makes
get
perfect
value
sense. This makes perfect
using
sense.
using a register that's already filled with a constant, right?
Yeah, so in the unify process, yeah, we actually haven't checked that in the previous example of using zero instead of new. We need a case where we are trying to unify a variable with a number. That will mandate us to go to get value or unify value eventually.
Here's the problem, Lemos. This takes addresses, and numbers don't have addresses.
Well, let's see how the book fixes it, because the book is also telling us how to unify with constants.
The book's not gonna tell us how because the book has a low-level trick on its side.
I don't see what you mean, so I'm gonna look at it.
Like, if you were going to implement this compiling to machine code and you had a proper binary representation, this would actually be indistinguishable from an address if you just pass it to get value, and it would work actually.
Yeah, so he is actually telling us how to implement for constants. Thank you, the book. So if you go to
It does?
page 131 in the PDF,
Oh, it's way down there.
yeah, it's in the cheating section, of course. Easy, easy, man. Uh, it doesn't explain how we're gonna get around the addresses problem. That's true. But it tells us how unify should be done with constants. So that's already enough.
Hmm,
Man, you can't you just type 131? You need to go yeah, okay. Yeah, there we
here.
go. Yeah, so there it is. It's a one-liner, in fact.
If D1 is different from D2, okay, but this is doing derefs on the PDL.
No, it's
Wait,
down there. Just keep going. If there you go. It's the case T true. We are only doing the reference and the structure case right now.
if T1 is a reference,
If
we
T1 is
bind.
not a reference and T2 is a constant, then we do this thing.
That is, this means actually that hmm, this means actually that we need to
Well, but the procedure still uses addresses. So we how are we gonna get around that problem?
yeah, we actually need to this is so annoying. We need to make it not use addresses essentially.
That's gonna suck ass, man. That's gonna suck ass.
Welp.
Uh, hmm. Do we really need to do that?
To do, make this work with non-addresses. Problem solved.
Man, but I'm still a little bit skeptical that we can't get around. What are we holding? We're holding raw values in the case of constants, right?
Yeah.
We're holding
Basically, we
raw
need to make
values.
basically we need to make this thing work with arbitrary cells instead of addresses.
That's gonna fuck everything, man. Everything in this function surrounds around the fact that those things are addresses.
That is true, but it's also what we got to do, unfortunately.
I don't know if I buy that, to be honest. Can't we just try to do some...
Look, it's pushing A1 and A2 into the PDL, then popping the PDL twice, so it's going to grab these two first, right?
Yeah.
Then it's dereffing them. And if they are different, then if one of them is a constant and the other is not a reference,
Can't we just get
the
around
values
by
must
using the ref
match.
cell instead?
No, because the argument type is wrong.
No, no, no. Well, assuming that A1 and A2 are actually cells instead of addresses. I don't know how we're gonna do the PDL
Then
trick, but the
no,
derefs...
yes, no, yes, we can. We just have to change some types around, but it should work.
Let's add the line on the T2 case for to finish for today then.
The T2 case. You mean this?
Yeah, with the constant. So, yeah, so if T1 is a reference, or
This is
T2
dealt
is a,
with.
yeah, this
Yeah,
is
no, this is
already
dealt with
there.
here.
Yeah. So if T1, no, T1 doesn't need to be a constant. T1 doesn't need to be a constant. That's actually what we're gonna check.
T1 doesn't need to. We're already checking this in the pattern match though.
Okay, that makes sense. And then we just
Then
compare L and R and R. Is it, and fail equals to that. Computer with fail equals to. That was very easy. Holy fuck.
yeah, yeah.
Okay, if T1 is not a constant, this is not gonna match and it's gonna go all the way to 182 and it's gonna fail. If they both are constants, then we compare their...
The
Oh,
contents.
wait a moment. That's not no, actually that is what we need to do. I take that back. Yeah. No, in the book it's written a little bit differently, but that's because we're using a better language. Okay. Okay. Man, I'm so I really wanted to see the integer thing working, but okay, I guess I'm gonna finish the recording now.
All right.